Okay, let's make a start. Right. So just as a quick recap, yesterday we went over the general structure of an atom and how it's made up of protons, which are these positive particles, electrons, which are negative particles, and neutrons, which are they don't have any charge. And another key thing we learned about is where these types of subatomic particles are located in an atom. And remember, the protons and the neutrons are at the center, and the electrons are sort of orbiting the center. We call that center the nucleus. They're on the outside in what are known as shells. And then another thing we talked about is the fact that electrons determine sort of the chemical nature of the element in terms of how it chemically reacts with other elements and the bonds that they form. And so we're going to go into more detail on that today because we also talked about the periodic table and how the periodic table came to be, and that some people in the past, for example, Dmitry Mendeleev, noticed patterns emerging with the elements, and that information can also be shown on the periodic table. So, to start off with, if you, and I'm going to link it now, if you get open the periodic table, AQA periodic table, let me link it for you guys. Right, here we are. Have that window open. Remember, at the very top you could rotate it just so then you don't have to adjust your head position to be able to read it properly. So this periodic table is the format in which you would get it in exams. Notice that when you compare it to other periodic tables, it looks slightly different. That's because it's been trimmed down a bit. But don't really be worried about that. I want you to get used to this particular periodic table because this is the one you're going to be using the most often. Okay, so if we remember, last time we talked about what all of the information that's in each little block means. So you do have a key provided for you at the top-ish, but remember the top number is going to be the atomic mass, relative atomic mass I should say, and the bottom number is how many protons we have. And that number is going to be unique because remember the number of protons determines what the element is. Okay, so we're going to be quickly, just to start off with, focusing on group 1. So that's the column all the way on the left-hand side. Oh, before I move on, let me just quickly link you, because there is a notes booklet for this. If you wanted to use it, let me just quickly link it again. There we go. Okay. So if you go on there and click the Word document files, because that way you can type things in, that'd probably be a bit more useful to you. Just giving anybody a little bit of time to prepare and get started. So it'd be useful for you to have a link open to the periodic table as well. Alright, so we're going to focus on the leftmost column, which is group 1. You see the group numbers at the top of the periodic table where it goes 1, 2, and then it skips all those elements in the middle, 3, 4, 5, 6, 7, 0. So those are the group numbers and they represent the columns. So when we talk about group 1, we're talking about column 1. So group 1 elements, they actually have a very special name. We call them the alkali metals. These are the alkali metals. And the reason why we call them the alkali metals is because when you put these elements in their pure form in water, there's a chemical reaction and the result is something that is alkali. Remember back in year 7 you talked about acids and alkalis? So basically if you put sodium in water, watch the chemical reaction happen, and then you tested the water with a bit of universal indicator, you will notice that it will turn blue, representing that it is an alkali. So we call these the alkali metals because when they react with water, they form like an alkali solution. So we have to know the properties of our alkali metals. What do they all have in common? Because remember, the people who formed the periodic table, they noticed patterns emerging. And what they noticed was that there are these elements, these alkali metals, they all belonged in group 1, and they have a lot of things in common. So the first thing that we have to talk about is the reactivity. Mainly, reactivity, just to put in brackets, it is how easily or violently it will chemically react. So that's what reactivity means. Now the alkali metals, they are all very reactive. So they have that in common with each other. They are all very reactive. But what I want you to notice, and I have it on the left-hand side of the notes booklets here, as you go down the group, as you go down that column, it gets more and more reactive. So, reactivity increases down the group. So what that means is potassium is more reactive than lithium, rubidium is more reactive than potassium, and the most reactive out of all of them is francium down here. So it is basically like an order of reactivity, a mini order of reactivity based around the alkali metals only. So we have the reactivity going down the group, it increases down the group, and now I'm going to talk about why. If you remember, we discussed the electronic structure yesterday of our first 20 elements. Let me just write down from the periodic table the atomic numbers, which is the number of protons, and if it's balanced in terms of charges, also the number of electrons. So lithium has 3 electrons. Just to shorten, instead of me writing electrons out, I'm going to write E and then negative on here. So lithium has 3. Sodium, if you look on your periodic table, that bottom number is 11. So sodium has 11. Potassium 19, and I don't want to go beyond that, so I'm going to leave it at that. You'll see the pattern from just these 3. So if I were to draw out the electronic structure, so where the electrons are in lithium, remember that the first shell can only hold 2 electrons, second shell can only hold a maximum of 8, third shell can hold a maximum of 8. So with lithium, first shell is going to have 1, 2 electrons. Lithium has 3 electrons, so there's one more that I need to put on. But remember, it can't fit on the first shell anymore because it's reached its maximum. So it's going to go on the outside there. And there's going to be a lone electron on the outside. That's lithium. Sodium has 11 electrons I need to put down. So 2 are going to go on the first shell. It had 11 electrons, so there's 9 left to put down. A maximum of 8 on the second shell here. So far I've put down 2 and then 10, but remember I had 11, so there is 1 spare electron on the outside. And then potassium 19. Two electrons down, then 8. So I have 10 electrons down right now, but it needs 19. And then another 8. Now I have 18 down, but remember I had 19 electrons that I need to put down. So once again, there's going to be 1 spare electron on the outside. We briefly touched on this yesterday. So group 1 elements, they all have 1 spare electron on its outermost shell. Now if you think about this and relate it to the reactivity, now it starts to make a bit more sense. Because since there's 1 extra electron on the outermost shell, it's only just one off having a full shell. All of the atoms, they prefer having full shells because that is when it's the most stable. Because it is completely full, it is satisfied. It's like eating a meal where you're not too stuffed, you're not still a little bit peckish, you're completely satisfied. So when it has a full shell, such as having a shell being 288, then it's happy. But for our alkali metals, all of them are just 1 electron more than being a stable full shell. So what ends up happening is because they're just 1 electron off of having that full shell, they tend to be very reactive because they want to lose that electron. They want to give that electron to someone else so then they can just be a stable full shell. So for example, lithium wants to get rid of that electron and then just become like that. Sodium wants to get rid of that electron and then just stick to those first 2 shells. Potassium want to get rid of that electron, just stick to those first 3 shells. It wants to have a full outer shell rather than just that 1 spare sitting there. Now if you notice, I said reactivity increases down the group. And the reason why that happens is because notice how our atom actually gets bigger and bigger as we move down the group. Like we start off with lithium, quite small, then sodium, then potassium, and it's getting larger and larger because every single time, notice that I'm adding like an extra shell on, an extra ring on. So that makes it more reactive because remember the very center of the atom is a positive charge because there are protons there. So the center is positive charge for all of these atoms. And these electrons are all negatively charged. Remember, positive attracts negative. So the nucleus sort of holds the electrons to it, keep the electrons because its positive charges attract the negative charges. Well, if you think about like potassium, for instance, let me use a different color so you can see clearly. There we go. Right. Look at potassium here, down here. The center is a positive charge, so it's going to attract these electrons to it. Because it's positive, electrons are negative, so it's keeping those electrons near the nucleus. But look at this little outer electron here on its own. Because it's so far away from potassium, because of the size of potassium, its attraction to the nucleus is not going to be as strong as, say, this electron's attraction to the nucleus. If an electron's closer, it's going to experience a greater attraction to the nucleus than it is if it was on an outermost shell. And also, if you think about how there's a bunch of other electrons in the way of this one being attracted, this is not going to experience much of an attraction at all. Not much attraction to nucleus. So it's not going to experience that pull from the nucleus, keeping it with that atom. Which is why this electron then would be very, very easy to lose. Which is why it is more reactive than the elements before it, because it's a lot easier for that electron to then go away and form a chemical reaction with something because of how far away it is from the nucleus and how there's other electrons in the way of it, so it doesn't really experience that much of an attraction from the protons in the nucleus there. We're going to go into this in a bit. We're going to go over that again, just so then you fully understand, but we'll do that in a little bit. Right now, I just want to move on to the properties. So with our alkali metals, what density means, remember, is how tightly packed the substances are how tightly packed the particles are in the substance. Why is my thing not writing? Where's my pen? There we go. Change color. So density, remember, is just how tightly packed particles are. Right, so the alkali metals are metals, but compared to other metals, low density. So I don't want you to just say that like it is completely not dense at all. I don't want you to just say it is just low density. It's in comparison to other metals. Like if you think about things like platinum or gold, they're a lot denser than the alkali metals are. Another note for the alkali metals is because they're a bit lower density, they can float on water. So if you were to put a chunk of lithium into water, it would float along the top. Same with sodium, same with potassium. It floats on the top because they're actually less dense than water. Now the real shame of distance learning is normally we would have this chemical reaction in class. So normally I would show you the reactions of lithium, sodium, potassium in class. I will link a YouTube video so you can see it on YouTube instead, but it is quite a good reaction. When we come back next year, I'll try to find, if I still teach you actually, I'll try to find a time to still do this experiment as a quick recap. So, in terms of their visible characteristics, even though they're a metal, they tend to be on the softer side, can be cut with knife. So even though they're a metal, you might think, well, you can't really cut a metal with a knife, but they are on more of the softer side. So it's easily cuttable with like a sharp knife, like a scalpel. And they all sort of have like a grayish, shiny appearance. But when it reacts with the oxygen and air, it might lose a bit of that shininess. So they have like a silvery gray, silvery shiny. Let me see how to do this in notes. Okay, so normally silvery slash shiny, but because remember it's so reactive, it reacts quickly with oxygen in the air and goes dull. So that's the general appearance of the alkali metals. They're all sort of silvery and shiny, but when you take them out and they're exposed to air, it can go a little bit dull because it's so reactive, it actually starts chemically reacting with the oxygen in the air. Which is why when we store alkali metals, next year when you see me do this in class, if you do have me, they're actually stored in oil to prevent that reaction with the air. Otherwise, our alkali metals that we have in the storeroom would just end up, chemically reacting with the oxygen and then going dull. Now, when it comes to the melting points and boiling points of our alkali metals, that for metals, they're pretty low. So, once again, low for metals. It can't be that low because they're still solid at room temperature, but low for metals. So when compared to the other solids, the other metals that are on the periodic table, it's still relatively low. And when you go down the group, it gets lower and lower. MP and BP decrease down group. Just as a quick example, so cesium, which is CS, at 29 degrees turns to liquid. So at 29 degrees, which is like, we've experienced 29-degree weather before, that's when cesium, a metal, would actually turn into a liquid. So for metals, the melting points and boiling points can get quite low. Going down the group, that number just keeps getting lower and lower, meaning it's easier for it to turn into liquid than it would be for the elements higher up. So it's easier for cesium to turn into a liquid than it is for sodium to turn into a liquid, so on and so forth. Now the main thing that we do see when it comes to our alkali metals, remember I mentioned a little bit earlier that the reason why they're called the alkali metals is because when you put them in water, they chemically react to form an alkali. And so the first key thing I want you to understand is that they all react with water, and they actually react quite violently with water. You'll notice them float on the top because they're not very dense, and they start fizzing around. At least. Some of them would have more, but most of them would fizz around at least, and this fizzing shows that a gas is being made, and that gas is hydrogen. When you get to potassium, though, which is just the third one down, if you put potassium in water, it's so reactive. Remember, its reactivity increases as you go down the group. When you hit potassium, it's so reactive that it actually bursts into flame. And it even gets more and more reactive as you go down that group. I'll put a YouTube link after this page. Now, when you... Oh, I should also say, after reaction, water goes alkaline. Oh, I shouldn't say water goes alkaline. The solution goes alkaline. Let's draw that. The water is just neutral, but a solution would go alkaline. Just nitpicking. Alkaline solution left. Okay. So now with the non-metals, they easily react with non-metals. Remember, the theme is that it's very reactive, so it reacts easily with non-metals. Remember I said that we store it in oil because it will end up reacting with the oxygen in air? Yeah, that's why, because it reacts so easily with non-metals. And as you can imagine, once again, as you go further down the group, it becomes easier and easier. So even though there's a lot of information here, what I want you to understand is that all of it pretty much has the same theme. In that the alkali metals in general is that they're all very reactive and that reactivity increases down the group. The reason why there's that change is because of how much bigger our alkali metal gets as we go down the group. So the one lone electron on the outermost shell becomes more and more. Hang on, I cut off then. That one lone electron on the outermost shell becomes more and more easily lost. This ends up with giving us a few properties. For example, when we put the alkali metals in water, they all sort of fizz and float on the top because they're not very dense. But as you go further down the group, you're going to see bigger and bigger reaction. When you look at the reactivity with nonmetals, because they're so reactive, they react easily with nonmetals. But that becomes even easier and easier as you go down the group. So same themes here. Melting points and boiling points, they're quite low. Becomes easier and easier to melt or boil as you go down the group. So a lot of that same trend. Okay, now I'm going to link you to a YouTube video. This is a classic. It is 3 minutes. So I'm going to give just a few minutes time for you guys to watch this video quickly because it is really, really good. So these are the alkali metals. I just want to show you this because I want you guys to understand that when I say that it reacts violently or that it bursts into flame, it's not a small thing that I'm talking about. It is quite a large reaction. So I'll give a few minutes for you guys to watch that. We'll go with, it's 3-minute video, so I'll give you like 5-6 minutes. Okay, just waiting 1 more minute for people to finish up with that video. But the main key thing is the alkali metals are very reactive when it comes to water. And notice that they use the bottom two, so the lower down alkali metals, instead of the top ones. Now the top ones just give a decent enough reaction, potassium bursts into flames, but then as you go further and further down that group, you get a more and more violent reaction. Okay, let's start back up. Right, so key thing is alkali metals, very reactive, especially when it comes to water. Alright, so now we're on to the halogens. And halogens are on the periodic table, the second to last group, group 7. Those are the halogens. And before we talk about the properties, I want you to notice how the reactivity, the arrow, is going in the opposite direction to what it was with the alkali metals. So alkali metals, the reactivity increases as you go down the group, but the halogens is the exact opposite. The reactivity increases as you go up the group. So in this case, fluorine is the most reactive, and astatine and iodine are the least reactive ones, whereas it was the opposite way around for the alkali metals, where francium and cesium were the most reactive, lithium was the least reactive. So the halogens, group 7, are the opposites to group 1 in terms of reactivity. Now I'm going to just show you why in terms of electrons. First, I just want to establish, remember, that chemical reactions happen because of the gaining or losing of electrons, because of how easily electrons will go off and react with another substance. So, fluorine has 9 electrons, so what I did was I just put a positive sign there to represent the positive nucleus. Remember 288, so 2 on the first shell, and there's 9 electrons, so there'll be 7 on the outermost shell. Notice that 7 means that there's space for 1 electron spare before it can make the full shell of 8. Same thing with chlorine. I'll just do fluorine and chlorine for now. You guys will understand the trend as we go down. You just add another shell. So chlorine has 17. So 2 electrons there. I have 15 electrons left to put down. 8 electrons on the second shell. 3, 4, 5, 6, 7, 8. So that I have 10 electrons put down, and then I have 7 electrons left to put down on the outermost shell. 1, 2, 3, 4, 5, 6, 7. Once again, notice that there's space for 1 more electron on that shell before it becomes that full 8 number. So what that's going to mean is that our halogens, our group 7 elements, are really going to want to have 1 more electron. They are going to be searching for that extra electron because they only need 1 more before they have that full shell of 8. Which means that they're going to be quite reactive, very reactive. And remember, the positive center is attracting electrons because it's positive, and the electrons are all negative. When you have a smaller element, such as fluorine, and this is chlorine here, let me label this. When you have a smaller element, such as fluorine, notice that the space for the electron is going to be closer to that positive charge. And there's not many electrons in the way blocking or shielding the positive charge, the blocking or shielding that attraction. Whereas if we want to put an electron here, it's pretty far away and also has quite a few electrons in the way that sort of shield against that positive and negative attraction. So when it comes to, if we say we had a spare electron here wandering about, and it doesn't know whether it's going to head over to fluorine or head over to chlorine, it's going to end up with fluorine because it's going to experience that greater pull from the nucleus with fluorine than it is from chlorine. Even though the positives are still positive, it's positive and positive, because it's a lot closer and there aren't as many rings in the middle shielding and blocking that attractive pull, we end up with electrons being more likely, outside electrons from another element, more likely to chemically react with the smaller ones because of that attractive pull from the nucleus. Which is why we get that opposite effect, where fluorine is going to end up with being the most reactive, whereas the larger ones are going to be less reactive. So reactivity is going to go up as you go up the group instead. Now on to the general properties of halogens. So halogens, they're actually they're they're a mix of they don't look the same at all because they all have different colors. So they produce colored vapors. Oh, I should draw a different color actually. The yellow wasn't working. So they all have different colors. They don't look alike. At first glance, you wouldn't put them all in the same group, but chemically, because their properties are the same, they do belong in the same group, but you wouldn't at first think it. They all have low melting points and boiling points. I'm going to put MP for melting point and boiling point. My melting points and boiling points are down here just to show you. So notice how most of them are in the negative zone. Now, one common exam style question, just to get you thinking and analyzing the data, is room temperature 20 degrees. If I were to say which element is going to be a solid at room temperature, have a think looking at the table which it's going to be. Which one is solid at room temperature from our melting and boiling points? Which is solid at room temperature? Spot on, Ruben. It is iodine. Now, the way you think about this is in terms of analyzing it in your head, is the lower the number, the easier it is for it to have melted. So for example, fluorine melted, it turned into liquid at negative 220. Iodine takes a temperature of 114 degrees for it to melt and turn into a liquid, which means that iodine before 114 was a solid, after 114 was a liquid. That's what melting point means. It's at what temperature it's going to go from solid to liquid. Now, if we look at the bottom row, what number it's going to take for it to go from a liquid to a gas, my question to you is, which ones are going to be a gas at room temperature? There are two. Which ones are gases at room temperature? So bottom row, Which ones of these are gases at room temperature? Spot on. Once again, Ruben, well done. It is fluorine and chlorine are going to be gases because they boiled all the way down in the negatives, meaning they already became gases way low, whereas we're going to have to heat things up to 59 degrees before bromine turns into a gas, and we would have to heat things up to 184 before iodine turns into a gas. So, one thing I also want you to make a note of is how they're all different states. Like, whereas the alkali metals, they were all solids. When it comes to the halogens, some of them are solids, some of them are liquids, some of them are gases, which is why I said that at first glance they might not look like they belong in the same group, but they do because of that because of their electronic structure. Okay, now here's a phrase that I need you guys to be aware of. Diatomic molecules. Di, the prefix di, di, means two. Now the definition of diatomic molecules, basically elements that come in pairs in nature. So what that means is basically, remember how we talked about how reactive, I should say properties of halogens, very reactive. Because of the fact that it only needs that one extra electron to be able to make a full shell, same as the alkali metals. Alkali metals has one extra electron it wants to lose. Halogens have one extra electron they want to gain. So they are going to be very reactive because of how close yet so far they are from having that full satisfactory full shell. So because of the fact that they're so reactive, you're not going to find any of the halogens in nature on its own, which is why if you notice the table, I have F2, Cl2, Br2, I2. Why I have those is because it's so reactive that it just does not exist on its own in nature. You won't just have one chlorine molecule floating around. You're going to have the two chlorine molecules bonded as a pair going around. So chlorine gas is just a bunch of chlorine molecules paired up. And we call that being diatomic molecules. Basically, because it's so reactive, it's just not going to exist on its own. It wants to be chemically bonded to something. Has to be. And there are some other elements that are also diatomic, like the halogens. It's not just halogens that are diatomic. The way I remember which elements are diatomic is have no fear of ice cold beer. So have, H stands for hydrogen, N is nitrogen, F is our halogen fluorine, O is oxygen, I is our halogen iodine, C is chlorine, our halogen, and beer stands for bromine. At this stage, you don't have to memorize it as much, but just keep that in mind that there are some elements that are so reactive that they just don't exist on their own in nature. Okay. Now spotting the pattern in the melting and boiling points and relating that to reactivity. So if you remember, from our alkali metals, as we go down the group, the melting and boiling point lowers, meaning it's more easy to melt it, easier to melt it, easier to boil it, because of the lower temperature is required. Once again, opposite is true for our halogens. The numbers get lower as you go up the group. So it's easier to melt and boil fluorine and chlorine than it is iodine. So our pattern is melting point and boiling point decreases as you go up the group this time. So notice that comparison between the alkali metals and the halogens. They are opposites to each other in that way in terms of reactivity, and it's all to do with that needing to gain or lose an electron. Now, this table down here, you don't need to memorize it, but this is just a table of information to give you an idea behind that reactivity. So this is just an example in terms of how our halogens are going to react with hydrogens. So notice explosive even at -200 and in dark, explosive in sunlight but slow in dark, only at over 300, only at over 300. So basically, in this little table here, my most reactive ones are at the top, my least reactive ones are at the bottom. And that coincides with the positions of our halogens. So through experiments, we've actually determined that order of reactivity, where fluorine at the very top has the most reaction. With hydrogen, it's actually explosive. But we do the same for iodine, which is near the bottom, and we need to have only specific conditions. We need to heat it up a bit, have a catalyst, and even then it's still slow. Even then it still does not really want to chemically react. So, halogens. The opposite goes when it comes to the reactivity. The reactivity increases as you go up the group because of that attractive force from that nucleus. When you have a smaller element, you're going to experience that greater attraction. The outside electrons are going to experience that greater attraction. Very last thing before we're done. Last thing, because this is just going to be a recap now. So I mentioned this the whole way through, why we have these patterns that we do. And the reason why we have these patterns that we do is briefly touched upon something known as electron shielding. Basically, if I were to draw it out, let's say this is an electron here. Let me draw out a different color, actually. This is my analogy. Okay. Electron shielding. Our nucleus is a positive charge. And our electrons on the outside here are negatively charged. Let's say that our nucleus, which has that attractive positive charge, let's say that nucleus was like a supermodel. There's my supermodel. She's going to represent my nucleus. Being a supermodel, she has flocks of admirers that are attracted to her and want to be around her. Unfortunately, because of bodyguards in the way, only 2 people are allowed to be the closest to her. Let me draw them in a different color. These admirers of hers are electrons. And the reason why they're attractive is, remember, the nucleus is positively charged because it has protons in there which are positive, neutrons which add nothing. So it's just pretty much protons that have the charge, and electrons are negatively charged, and there's a positive-negative attraction. So we have our admirers. Now, let's say that we have another group of admirers on the outside. Okay. If I kept drawing more and more people, so more and more shells of electron admirers, eventually this guy over here, this dude, he's going to be so far away that he can't even see her because there's all these other electron admirers blocking his view. So he just isn't interested anymore. There's too many people in the way. You know what? Forget it. Don't want our attention anyway. I'm out. I'm gonna go and get myself some lunch instead. That's what he's thinking. Whereas the ones who are closest, because they're right in front of her, they're going to experience that greater attraction. So electron shielding is basically when you have like a ring between the outermost shell and that attractive nucleus center, attractive positive center in the nucleus. Every time you add another ring between the outermost shell where the bonding's going to happen and that nucleus, you're going to get less of an attractive effect. So basically, we call them the inner shells. So the shells that are not on the outermost, inner shells of electrons, shield outermost shell, where the electrons are lost or gained, from nucleus's attraction. And then also another thing is just being further away. That's gonna make it so then it's less attraction. Less attraction. Okay. So once again, this leads into our reactivity patterns, which is why it happens, why we have the alkali metals increase in reactivity as we go down the group, and why it's opposite for group 7, our halogens. When we have our lithium, we have the smallest alkali metal. This is the outermost electron that wants to leave because it's far off from being a full outer shell. It's all on its own. But it's going to be experiencing that attraction to the nucleus. And because it's closer, and also because there's only one other shell in between, it's still experiencing a good amount of attraction. But taking in the case of sodium, this is the electron that wants to leave. It is still experiencing an attraction to the nucleus, but it's further away, and there's two lots of electron shells in between him and the attractive nucleus. So it's going to be a lot easier for him to go than it is for this one to go, because of that less of an attraction to that nucleus. It's not as inclined to stay. Opposite is true for the group 7. It's wanting to gain that extra electron, remember, to make that full outer shell. When it's larger, the electron is not experiencing as great of an attractive force because of the electron shielding. We have two shells here shielding the attractive force, and also it being further away, it's going to experience less of a tug to the chlorine. But it's going to experience a greater tug to the fluorine because it's, number one, it's closer, and number two, there's only one shell that is shielding the attractive force. So it's going to be going to the fluorine rather than to the chlorine. Fluorine is smaller, it's near the top of the periodic table, so it is going to be more reactive than the chlorine is. Okay, so that is the periodic table topic done. You guys will be ready now for the topic test that I'm going to set on starting the 18th of which is this next Monday. It's just going to be once again a short 15-minute topic test for you to do, which isn't, it won't take you long, and attached to show my homework. So you do have all the notes now here for the periodic table test. Main key things is know the trend, know the pattern in reactivity of group 1 and group 7, and also know why in terms of protons, neutrons, electrons. Okay, so, right, have a good rest of the day, everybody. Half-term break is soon, and enjoy.